Evening, everybody. It's 5 o'clock on Thursday, and we got some calculus to do. Today's kind of nice. We only got one section, so it'll be more. Feels like it sometimes, right? So today we only got one section to do. It's going to be kind of nice. Hopefully, it'll feel a little bit less rushed. We're doing the other form of multiplication today, the cross product. Want to mention you guys did great as far as uploading your work from last class. That's exactly the way you do it. You put the section number and the problem number or numbers. I like how you did multiple problem numbers. So if you did 3 and 4, you put them both in there. I thought that was great. The only comment I had was depends on what time zone you're in, right? Whether or not it's morning. The only comment I wanted to make, this is going forward, anytime you submit anything up there, don't submit Word documents, only because sometimes if you have a different version of Word, when people open it, it can look different. So just convert it to a PDF before you upload it, okay? Real easy to do. You do go into Word, you go to File, Save As, and you just select the PDF file type. Because that's how, when we go to do the take-home problems, you'll turn them in as PDFs. Oh, guys, don't worry about it. This is new for all of us, and I didn't put that in as a guideline. But as a general rule of thumb, and this isn't just for this class, I would recommend it for any of your classes. When you're submitting, if you're submitting a paper or something, I recommend submitting it as a PDF unless your teacher tells you otherwise. And again, the biggest reason is because if I have a different version of Word than you, when I open it up, it could screw up the formatting. If we have different fonts installed, it might look different. If you convert it to a PDF, much, much, much higher probability that what you saw on your screen is what I'm going to see on my screen. But guys, do not worry about it. We're still in only the second week. We're kind of still really getting used to how this class is going to go. And that's why we're only doing one section today. Give you a chance to catch your breath before next week. And things are going to start picking up a little bit next week. And then when we get into chapter 13, it's when we get into the really cool topics. So one thing I want to mention, and I'll mention it again at the end, next week we'll start doing a little bit of calculus, in particular, some derivatives and integrals and antiderivatives. So if you need a refresher on your derivative and antiderivative rules, this weekend would be a good time to go over those. One way of doing that is to go through the review in more, the Calc 1 and 2 review that's not due till the end of the semester. Do any of the problems that are derivative and antiderivative practice. And then once you're done with that, if you want more practice, you can find some sheets of derivatives and antiderivatives online. You just need to have those basic rules, your power rule, your exponential rule, your product rule, your quotient rule, your chain rule, forward and backwards, because we won't have time in here. It's not a quiz. It's just a review, so it's not timed. And you have until the end of the semester to do it. So it's not timed at all. You can go in and out as you please. Do the problems you want to do, skip the ones that you don't need to do right now. So take advantage of this weekend, since we only have the one section today. For those of you guys who could use a little extra practice with your derivative rules, because we won't have time in here to practice them. Okay? All right. That said, let's talk about the cross product and there's not a lot to say. This is a pretty short section. As you saw most of it in the videos. I'm going to mention a couple of things on the highlights, and then we're going to go through the worksheet. All right, so I like to start off talking about cross product by talking about torque, because it's something we can all relate to. It's a measure of how much force is acting on an object that causes the object to rotate. And the object rotates around an axis called the pivot point. Don't worry, guys, you don't need to know these definitions. I'm just giving you these so that we can define cross product. And it depends on the force in the direction of movement and the distance the force is from the pivot point. All right. Now, the nice thing is we can represent the force and the distance as vectors. The force vector is in the direction of the applied force, and the distance vector points away from the pivot point. What do I mean by this? Well, the most common example, I think an example all of us can relate to, is if you're trying to, maybe unscrew or screw in a bolt with a wrench. So let's talk about it in terms of a wrench. And there's our pivot point. So we're going to apply a force to this lever, and this lever is going to rotate around this pivot. Maybe we're trying to screw in or unscrew a bolt. So you can think of this as a wrench. And we have a distance vector, which is the distance from the pivot, and then our force vector. And basically, the cross product actually gives us the torque. But the reason I like this example is it's something that we can all relate to, because we've all tried to rotate a lever around a pivot point. If you haven't tried, using a wrench to unscrew or screw something in, even a steering wheel gets spun around a center pivot point, and that's torque that you're applying to spin the steering wheel when you're turning. Now, a couple things we know about torque from having done that. We want to push as perpendicular as possible to the lever to get the most torque. And the further we are from the pivot point, the more torque we'll get. If we try pushing in here towards the pivot point, it's really hard, but that's why a lot of times you see those really long wrenches, because we can get a lot more torque. So what that means is we need the perpendicular component of F. So when you see this notation here, if you're not familiar with it, this means perpendicular. So this means F perpendicular. What that means is it's the component of F that is perpendicular to our lever. That's that blue guy right here. So we need this component of F, because that's going to be the one that does the pushing on this lever. The component that's parallel, that I'm not going to put on here, doesn't do anything, doesn't have any effect on the lever. All right. Now, let's think about how we would calculate F perpendicular, because we have a right triangle. We were talking last time, all these vectors end up as right triangles. So if we have some angle theta, so that's the angle between our force vector and the lever. Well, notice that we have the opposite side, and sine relates the opposite side and the hypotenuse being our force vector. So we're going to be able to use sine to get this, because that F perpendicular component is going to be the vector F, its magnitude, because that would be the length of this vector, times sine of theta. Again, that comes from right angle trig. So just as a little, reminder, right? Sine theta is opposite over hypotenuse, which for us, the opposite side is this F perpendicular over F. And, I should have magnitude signs in there, because it's the magnitude of those vectors, because we want to be a scalar quantity. So solving that for F perpendicular, we get that the magnitude of F times sine theta is going to give us that component of F that really does all the work in moving the vector, right? I think that's one of the cool things about vectors. You guys have all taken trig. It's really just a lot of right angle trig. And what this does is it gives us the geometric definition for cross product. All right, so it's the magnitude of R, so the distance we are from the pivot point, dotted with it's not dotted. Sorry, this is not a dot product. It's actually, this time it's just multiplication. I know that can be a little confusing. Here's why we know it's multiplication, not dot product. We're taking the magnitude of these vectors, which makes them scalars. You can't take a dot product between scalars. Dot product is reserved for vectors. So that's why we know this dot is just multiplication. So what we would want to do is multiply the distance from the pivot times the perpendicular component of f, which we now know is the magnitude of f times sine theta. This is our geometric definition of the cross product. If we know theta, so if you're in a situation where you know theta, torque is a good one because you could say, oh, there's a force pushing on the lever at a 30-degree angle. Well, hey, if you know theta, the geometric definition is very easy to use. We will have an algebraic definition as well, just like with dot product, which will be the easier one to use if our vectors are in component form. But if we already know the angle between them, we'll use the geometric definition. All right. Now, there's some cool things that are going to fall out of us now having the geometric definition. So let's talk a little bit about the geometric definition. So cross product, like we talked a little bit about this last time. We use the X for cross product, the dot for dot product. And we know that they're vectors because of the little hats on top. So if we were doing A cross B, well, think about the properties. Here's its magnitude. It's the magnitude of A times the magnitude of B times sine of theta. And one thing to note about the cross product is it gives you a vector as a result. If you remember, the dot product gave us a scalar as a result. The cross product gives you a vector as a result with a magnitude of magnitude A, magnitude B, sine of theta. And the direction is perpendicular to the plane created by the given vectors. All right. Now you saw in the video that there's the right-hand rule to determine the direction of the vector. All right. So let me show you, there's a couple different ways to do the right-hand rule. I'll show you, let me put on my camera so you can see how I would do the right-hand rule on this one. So we're doing A cross B. Now, here's the thing. A cross B, if we assume that A and B are in this plane that is the screen, there's two vectors that are normal. One's coming directly out of the screen toward us, and one is going into the screen away from us. So the question is, which of those two perpendicular vectors do we get with the cross product? And that's where the right-hand rule comes in. So let me show you how I would do the right-hand rule on this one. All right, so what I would do is I would take my hand and I put my fingers in the direction of the first vector. So since I'm doing A cross B, I put my fingers in the direction of A, curl them in the direction of B, and then my thumb tells me which direction the normal vector is pointing. So in this case, if we were doing A cross B, the normal vector would be coming out of the screen towards us. If we were doing B cross A, I put my fingers in the direction of B, curl them in the direction of A, thumb goes into the screen. All right, that's the way I've always done right-hand rule. There is another way of doing right-hand rule. Right-hand rule is not going to be super important, and it's definitely not going to be something you need to know for the exam. I'll show you another way of doing the right-hand rule, and it's kind of up to you. It's kind of a user's choice. I like that. I like fingers in the direction of the first one, so in the direction of A, curl them in the second, and my thumb tells me the direction. The other way is this way. You can use your index finger and your middle finger, and so this would have been in the direction of A. This would have been in my middle finger here would have been in the this is my index finger in the direction of A, middle finger in the direction of B, coming out of the screen. Okay, so it's kind of whichever one you prefer. most of the time, there's not going to be a case in here where that's going to be a huge issue. Because most of the time we're going to have our vectors in component form, and that's where it's a little bit easier to get the direction. Okay, so that's the right-hand rule. Again, you know, don't worry about trying to memorize the right-hand rule. If you get into if you get into a situation where you need to use it, just look it up. But you know, it's not going to show up on a you're not going to have to perform the right-hand rule on a test or anything. So I don't want you to feel like you have to memorize it. All right, let's talk about the algebraic definition, because this is the one you're going to use more often. All right. So the algebraic definition is nice because this can be done from vectors when they're in component form, and then A cross B is the following, which I know looks like a mess. But again, I want to remind you guys, for the exam, you're going to have note cards. So feel free to put this formula on your note card. It's not something I want you to memorize. There's enough chances to make an error doing the cross product by hand, even with the formula. So I'm not going to add in trying to memorize that formula. So I don't want you to worry about memorizing this. All right. What's more important is that we know how to use it, know when to use it, and know what it gives us. Now, here's what's nice about the algebraic version. If you notice the format it comes out in, notice I don't have the magnitude bars here, and notice I have my vector notation. This is a vector. So when we do the algebraic definition, what we get is a vector, which means it already has magnitude and direction. So we don't have to do a right-hand rule. The direction will be defined by the components of the vector that results from our cross product. All right. So that's why I'm saying that memorizing the right-hand rule is not a big deal. Most of the time, we'll be using the algebraic definition. You know, you can also do the algebraic definition by computing a 3x3 determinant. So you would think of this as a 3x3 matrix. And we'll talk a little bit about the determinant here because it's coming up. Now, the determinant of a 3x3 matrix is not really going to be a topic we talk a lot about in here, so I'm not going to get into what a determinant is. If you have already taken linear algebra or are concurrently taking linear algebra, you're going to do determinant of matrices. If you're going to take linear algebra down the road, which is a lot of you guys, you'll be doing determinants of 2x2s and 3x3s and 4x4s. So I don't think it's a bad thing to know how to do one by hand. But again, when it comes to the exam, you can just use that formula right there if you like it. For those of you guys who like this way, that's fine too. Now, I do want to point out one difference here, and it's kind of an important one. It's this middle term. Notice here, it's A3B1 minus A1B3. But here, it's reverse. The reason it's reverse is because of this negative sign, pretend like that's an arrow, because of that negative sign right there. That negative sign flipped those two terms, and that's why these two are the same, even though that middle term looks different. No, you can't. You won't be able to do it on a calculator. And the reason is because the first row is IJK. They're unknowns. So you would need to use a calculator that could do symbolic manipulations. You know, a TI-84 can do 3x3 matrices, absolutely, and it can do determinants of 3x3 matrices, but all the entries have to be numbers. So let's see. Let's do one example of this, just so you guys have seen it. I know it's in the video as well, but I want you guys to, we got the time today, so let's go ahead and just take a look for those of you guys who want to use the matrix form. So let's say we got a couple of vectors. A is I'm not gonna make it anything too crazy. 1, 2, 3, and B is -3 to -1, okay? And we got to do the cross product. And we're going to do A cross B. Now, one thing about the cross product, and you kind of saw it with the right-hand rule, the order does matter. A cross B would give, you know, if you remember from the right-hand rule, A cross B gave us a normal vector out of the board. B cross A gives us a normal vector into the board. They both give us normal vectors to the plane that A and B lie in. It's just 180-degree opposite direction. So if we're going to do A cross B, here's how we would do it with the determinant of a 3 by 3 matrix. So you have I, J, K. For those of you guys who've done linear algebra, you've seen this before. For those of you guys who haven't seen it, again, it's not, you know, no, sorry, we're putting the components of A. I didn't want to do that. So A would be 1, 2, 3, and then B is going to go in here, -3 to -1. Okay, so what we do is we turn it into the determinant of a bunch of 2 by 2 matrices. So what you do is basically we look at this first I, and what we're going to do is we're going to kind of cancel out that row and that column, and that's going to be the 2 by 2 matrix that gets multiplied by I. All right. So that means I'm going to be doing a 2 by 2 matrix, 2, 3, 2, -1 times the I vector. Now, what you do is you switch signs every time. That's where this negative was coming in. So for a 3 by 3, we only switch signs on this middle one. Now, the determinant, now we always cross out this row. We cross out this column. And so now the vector will be 1, 3, -3, -1. All right. 1, -3, 3, -1. And then it goes back to plus. And if we had a bigger matrix, it'd go minus, and then plus, and then minus. Kind of swaps every time. Again, we cross out this and this, and so the last little matrix is 1, 2, -3, 2. Oh, I forgot the J. Thank you. Yep, I did forget the J. Let's get that in there. This one's going to get multiplied by J because that was what was in the top row. And then the last one is the determinant of, now it's going to be times K. So 1, 2, -3, 2. Let's see, I should have a little bit more room if I slide this over. No, I don't. Oh, geez. Sorry, guys. That K should have been, I should have had room for that. My whiteboard skills are so-so, as you can tell. Now, 2 by 2 determinants are actually pretty easy. What you do is, I kind of think of it like a fish. So again, this is more for, you know, so I kind of do a little thing like this, and it looks like a little fish because I do 2 times -1 minus 3 times 2. And that's the determinant of that matrix. So, and look at this, A2 times B3. So here's my little fish, A2 times B3 minus A3 times B2. So we have 2 times -1 minus 3 times 2 times I. Then minus, and this is going to be 1 times -1 minus 3 times -3 J, and I'm going to run out of room again. Let's see if we can get this guy in here. 1 times 2 minus 2 times -3. Yep, I ran out of room again. And we know that the K goes right there. Okay. So our vector is going to be, let's see, we got -2 minus 6. So we have a -8i minus, we have a -1 plus, it's going to be +9 because it's minus a -3. So -1 plus 9, so 8j. And then we have 2. And then this is going to be minus a -6. So 2 plus 6. So plus 8k. Or in our other form, -8, -8, 8. Okay. Now, guys, it is very easy to make mistakes doing the cross product by hand. All right. So there are a lot of cross product calculators out here, but Wolfram Alpha is a good one. So cross products of, what do we have? 1, 2, 3, and -3 to -1. And there it is, -8, -8, 8. All right. Which signs in particular, Trey? The signs will take a little bit of getting used to, because most of you guys have not done the determinant before. And again, guys, don't feel like you have to memorize the determinant of a 3x3 matrix for this class, because you do have the formula right here. But the way the signs work is when you break it into the, yeah, I know. And that's why, Trey, and that's why I recommend when you're doing homework, or especially when you guys are doing the take-home problems, if you're doing a cross product, no, do it by hand. You know, it's good practice, but check it with Wolfram Alpha or a cross product calculator, because Trey brings up a really good point, guys. It is so easy to just miss. Look at all the negatives I had going on here. I had a negative sign here and minus here, a minus here, and negative sign here. Okay, so it is very easy to make a sign mistake, and once you do that, it can mess up the rest of your problem. So by all means, you know, we have access to technology. Use it to check your answers as you're doing this. I just wanted to do an example of how you do it via a determinant for those of you guys who are interested in doing it that way. But guys, this formula will work just fine. And again, for the in-class part of the exam, you'll have a note card. So if you want, you can just put that formula right on there. But absolutely be careful about your negative signs. It's the most common mistake with the cross product. The cross product's not hard. It's just that we do so much multiplication and so much subtraction in addition, and there's so many positives and negatives going on. It's just real easy to make a little math error. So when you're working on homework, when you're working on take-home problems, when you're working on the worksheet in a little bit, check your answer in Wolfram Alpha. A lot of times it'll just be a sign error. You know, you made a small mistake. A lot of times what I see, 2 of the components will be correct and 1 of them will be off. But having 1 of those components be off can obviously throw off the rest of your problem depending on what you're doing. All right. So use technology to help you out because you have access to it. Questions at this point? All right. You guys are going to get a chance to practice this in about probably 10 minutes. We don't have much more to talk about. Just some interesting geometric principles, geometric things that come out of the cross product. All right, so if we had a parallelogram, all right, so a parallelogram, we can think of a parallelogram being formed by 2 vectors because I can draw parallel lines to those vectors and there is my parallelogram. If I wanted to do the area of this parallelogram, what I do is I multiply the height of the parallelogram, the perpendicular height, by the base. So the magnitude of A, and then that vertical line, let's drop it in there. Oh, I put it over here, sorry. That vertical line, well, where's that going to come from? That's going to come from the magnitude of B times the sine of theta, just like we saw in the geometric definition. So it turns out that the magnitude of the cross product between A and B gives us the area of the parallelogram formed by A and B as two of the sides. All right. So if you ever get asked, find the area of the parallelogram between two vectors, you just have to do the cross product and take the magnitude. And if you have the angle, you could use the geometric definition. If you don't, if A and B are given in component form, you do the cross product algebraically, and then you take the magnitude, which is the square root of the sum of the squares of the components, like we saw in the last lesson. All right. So a lot of the stuff just kind of builds on what we've been doing. Now, similarly, we could do the very similar thing. There's a triangle also formed by this. Well, notice that that triangle is exactly half of the parallelogram. So the area of the triangle formed by the vectors A and B is half of the magnitude of the cross product. So there's all these really cool things that come out of this. All right, the triple scalar product. So the combination A, now this is dot product because A is a vector and B cross C is a vector. This is called a triple scalar because the product results in a scalar. Now the magnitude of the scalar has a nice geometric meaning as well. It gives the volume of a parallelepiped, which is a box that is kind of slanted. This is a parallelepiped. You know, we can see we got a parallel side here and then a rectangular side on top. Rectangular side here. So it's 4 rectangles and 2 parallelograms on the end. Well, we know to do an area of a parallelogram, it's A cross B, right? So here's how this works. What we do is the base is a parallelogram, and so its area is the magnitude of B cross C. And then we need H, which is the height of the parallelepiped, which is the vector projection of A in the direction of B cross C, which, remember, B cross C gives us a vector that is perpendicular to the plane that B and C lie in. That's the H, that's the height of the parallelepiped. We know how from last time to do a vector projection, and that's A dotted with the vector V cross C. All right, I know the notation isn't quite the cleanest on this slide, but what it turns out is it's actually not that hard for us to do. So if we want to do the volume, excuse me, I don't want to go that far ahead just yet. If we want to do the volume of a parallelepiped, what we do is first we, geez, that's ridiculous. Come on. First we do B cross C, and what that does is that gives us this vector here, and then all we have to do is dot that with A, because that'll give us the vector projection of A in the direction of B cross C. The result of this is a scalar, which is the volume of the parallelepiped. That's all we have to do. So, and guys, this is not a formula I have to memorize. I'm not going to ask you the volume of a parallelepiped on an exam. This is just one of the cool geometric interpretations of a cross product, and in this case, a triple scalar. You might get one of these in the homework or on the worksheet, but I don't want you to memorize parallelepipeds. All right. Okay. So those are just some things that we can do with the cross product, and you're going to do these on the worksheet. And really, all it's doing is giving you practice at calculating the cross product. Now we have so just to finish up, we have 2 types of vector multiplication. All right. Both operations need two vectors, the dot product and the cross product. The dot product produces a scalar, the cross product produces a vector. Now, in each case, what do we think, if the vectors, what do we have if the vectors are perpendicular? Well, we know that the dot product we saw last time, if they're perpendicular, is 0. Now, in this case, the cross product, if we think of that torque example, torque is going to be a maximum if we push in a direction that is perpendicular to our lever. So the cross product is at a maximum when the two vectors are perpendicular. So there's these nice little differences between the two multiplications, and depending on what we're trying to do, we use one or the other. Dot product, one of its main uses is a vector projection. Cross product, one of its main uses is torque, or trying to find a vector that is parallel to two vectors in a plane, which we know from last time is called a normal vector. So the dot product we use for vector projections, and the cross product is used to find a perpendicular or normal or orthogonal vector to two given vectors. Next week, we're going to see how we can leverage the cross product to find the equation of a plane. And it builds off of what we did last time. If you remember, last time, we saw that if we had a line in the form ax plus by equals c, then its normal vector was AB. Well, same thing is going to happen with a linear function in 3D. If we have ax plus by plus cz equals d, then the normal vector is ABC. So if we know the normal vector, it's very easy to build the plane. I'm kind of giving you a preview of next week, so don't worry about that too much. But we'll be seeing the applications of the cross product right away next week. Now here's something else that we talked about this with the dot product. The dot product generalizes to any dimension. We can do the dot product with a 2D vector up to an n-dimensional vector. The cross product only exists in 3 space. So we can only do the cross product with vectors that have 3 components. All right. And both the geometric definitions involve the magnitude of the 2 vectors and the angle between them. With dot product, it was cosine. With cross product, it's sine. And that's why we get 0 for perpendicular with the dot product and a maximum for cross product at perpendicular, because cosine of 90 degrees is 0, sine of 90 degrees is 1, or at the maximum sine can be. Okay, guys, questions at this point?
Can you leave that slide up for a second?
I can.
Thanks.
Yeah, and feel free to take a screenshot of this. And don't forget the PowerPoint is in chat. So if you want to download the PowerPoint, feel free. And I'll also, let me give you the link to the whiteboard. So here's the link to the whiteboard that I was writing on in case you want that. Okay, so now you got the 2 pages of the whiteboard in chat, and you also have the PowerPoint as well.
I do have one more question.
Yeah.
So it says the cross product only exists in 3-dimensional space, but you only need 2 dimensions of vectors in order to get the cross product. Is that because you the third dimension or the third vector you get out of it is in the third dimension, I guess. I say the third dimension, then the Z.
Yes, yes, I
'Cause,
understand
like,
what you're saying, I think. So let me see
yeah.
if I
Okay.
get what you're saying and if this helps, and let me know if it doesn't.
All right.
So yeah, so we start with two vectors, right?
Mm-hmm.
And you know, let's say the whiteboard is our plane.
Mm-hmm.
And so let's put in, you know, so maybe we have a vector here. Stop. And a vector here. All right, so these are our two vectors, and they
Yeah.
lie in this plane.
Mm-hmm.
And so you're right. These are
Two-dimensional plane right now.
Say that again, Cooper.
It's two-dimensional at the moment. The plane is two-dimensional.
The plane is flat, so it is
Yeah.
two-dimensional, even though the
Mm-hmm.
vectors each have three components.
Mm-hmm.
And what happens is once we do the cross product, the third vector would either be coming out of the whiteboard towards us,
Mm-hmm.
or into the whiteboard away from us, depending on which one we do. If we do A cross B or B cross A.
Oh, but you need three components to do it in general. You can't do it with two.
Yes.
Okay.
Yeah.
All right. It could be like three, like vector A could be 3, 5, 0, and vector B could be 2, 4, 0. So it would be technically in two dimensions, but it still needs to have that third dimension.
They're all two vectors are always going to be able to lie in a plane.
Mm-hmm.
Let's see.
Yeah, I kind of get what you're saying. Like they could be in a plane even if they're all angled into the Z.
Yes, but they would still lie in some plane. It just may not be parallel to any of our coordinate planes.
All right, cool. That answered my question.
Okay, good.
Yeah.
It's a good question. You know, it's really easy to think about the vectors being in two planes when one of the components is 0 because they both maybe lie in the XY plane.
Mm-hmm.
But even if they have three components, and a couple of you guys probably saw this last time when you were doing the vectors in the Calc plot 3D. Once you put those two vectors in there, there is a plane that those two vectors lie in. So no matter what, if you only have two vectors with three components, there is a plane that they're both going to lie in. And that gets back to what you were talking about with it being kind of 2D. But once you cross product them, we're guaranteed that we're going to get a third vector that is going to be normal to them, which all of a sudden creates this third dimension.
Got it.
Other questions? All right, so here's what we're going to do, guys. Let's see, we got 14 today. Let's do 4. Yeah, let's do 4 groups. We'll do 4 groups. I'm not going to assign problems from this one because it is a shorter worksheet. And we got a good 45 minutes left. So you can start with number 1 and work your way through, or if you want to skip around, that's fine. And do however many you guys can in your group. And that's gonna, whatever you guys get through, if you get through 1 through 4 and don't finish 5, you can post 1 through 4. However many problems you guys finish, I'll give you credit for. Number 2, there's not really much work to show, so I wouldn't even worry about showing work for number 2. Just number 2 is more of a general answer, but 1, 3, 4, and 5 from the worksheet are all ones you guys can do solutions to. So do as many as you can in the next 45 minutes. If your group gets through all of them, if you've finished all 5 problems, call me in and we'll come in and take a look and chat and see how it went. Obviously, if you have questions, let me know. The answer key, as always, is going to be on the second page. But, there's no point. It's such a short worksheet, and we only have the one section. So let's take this time for you guys to practice with the dot product, excuse me, cross product, because when you go to do the homework, that way you'll have it down. And don't forget, feel free to use Wolfram Alpha or any other program out there to check your answers. but at least do one of them using either the formula or the 3x3 matrix method just for practice, because you will have to do at least 1 or 2 cross products on the in-class exam. So I do want you to have some practice doing it by hand. But if you do like number 1 by hand and you got it down, you'd rather do number 3 using Wolfram Alpha, totally fine. All right. All right, let me get you guys broken up into groups.
Mr. Clark?
Yeah, sorry, I was muted.
No, it's all right. Was there a typo on the answer sheet for number 4, or were you supposed to take the absolute value of the product of the J components?
For number 4, you take the absolute value because we're looking for volume. And
Okay, that's what I had thought.
yeah, yep.
So if you're doing that to get volume and you get a negative number, do you just automatically instinctually just absolute value it?
Yes.
Okay, so it'd be, instead of 14 minus 3, it'd be 14 plus the absolute value of negative 3.
Well, I'd have to see what your work is, but if you get a negative value for the volume, which could happen easily, because depending on which way you do your cross product, you could get a positive or a negative. Well, but you do magnitude, so it should come out positive. So the negative came on the dot product?
Yes. Yes.
Should have come out positive. Let me double check. Let me see what I. Yeah, you should have had a positive because, well, if you did it correctly, so you should have either gotten as your answer 17 or negative 17, depending on which way you did the cross product. And then you would take the absolute value of that.
So the cross product of B, for my cross product for B and C, I got 7, -3, and -5.
Right.
You
You did your cross product on different vectors than I did, so I don't have the numbers in front of me.
Oh, okay.
But if you want to hang around for a couple minutes after class, we can take a look.
Okay.
Okay, guys. We're at 6:30. Hopefully hopefully after doing some of those problems, you feel comfortable with the cross product. It's not that difficult. Like we were talking earlier, the biggest thing you got to worry about are the little math errors because of all the positive and negative signs going on. So just be careful of that. So when you're doing homework or, take home problems or anything, make sure you're checking your answers using technology. Again, for next week, we are going to start getting into some calculus. And then once we get into module 3, we're really going to be hitting the calculus. So for those of you guys who maybe need a little brushing up on your derivative and antiderivative rules, this weekend would be a good opportunity to practice. Sorry for going a little bit over. If you have questions, feel free to ask. I can hang around for a few minutes. And I know we're going to take a look at number 4 here. But if you don't, it's already after 6:30. When you're ready to post, don't forget to post your solutions. I go through and check those on the day of class. So just sometime before class on Tuesday, make sure you get those posted. All right. If you don't have any questions, I'll see you on Tuesday. If you have questions, let me know.
Thanks.
No problem, guys. Oops. All right. All right, Garrett, let's take a look. Can you see my screen?
Yes.
All right, let's see what we got here. We'll do this the quick way. All right, so which two did you cross product?
B and C.
Okay. Of 2, -1, 4. Because, the only difference should have been, if you get a negative, it should have been like a -17. So like you were saying, you take the absolute value of it. But what you were saying sounded a little different. So let's see what's happening. All right, so let's see.
Oh.
Is that what you got?
I got -3 instead of 3.
Okay.
How did I do that?
It's so easy to get a sign error. Which way did you calculate the cross product?
I just did it the A2 B3 minus
Okay,
A.
so from the formula.
Yeah, I'm just gonna take a look at it really fast and see if I can figure it out.
It sounds like it's just a sign error on that middle component. And again, it's easy. It's so easy to have happen. I have that kind of stuff happen too.
Yeah, I just switched it.
Okay. And
I did it backwards. I did B2 or I did B1 I did A1 B3 and then I did A3 B1. So
okay.
I got -2 minus 1 instead of 1 minus -2. So
and that's the one thing. Be careful because if you notice, like in my formula, right, it's one way up here and then it's another way down here, but that's because the negative's out front, which would have switched the sign on your -3 if you're using this method.
Yeah, I use that one. That's where.
Okay, that's all right. Let's make these mistakes now, right? That way we don't make them later.
Which is funny though, because I think I used the same one earlier, but still got the same answer. So I don't know.
Yeah, like I said, let's get these errors out of the way now, and when it comes test time, you'll have it down.
Yeah. All righty. Thanks so much for your time there. I appreciate it.
Yeah, no problem. I'm glad we figured it out. And now when you do the dot product, you should get a positive answer.
I'll never forget that.
Exactly, right?
All right. You have a nice night. Yeah.
You too, Garrett. Take care. I'll see you next week.